Okay, class. So let's try to understand now what deviatoric and volumetric stresses are as far as stress analysis is concerned. This is very useful not only in structural engineering but also in soil mechanics, no, in geotechnical engineering. So if we let sigma ij be the stress tensor at a point in y-I-x or y-I axis, so we can seek a system of coordinates y prime I such that the sum, okay, of the diagonal components of the matrix, whether it be a principal stress matrix or not, is actually assumed to be zero. So we are now targeting what you call a pure shear state condition. So this is very useful in getting the maximum, okay, the maximum shear stress that is available, no, in terms of the principal axis concerned. So we discussed the derivation of a pure shear state in terms of the NI direction in my previous lecture. So the form of the matrix will then be equivalent to this one here, wherein all your diagonal elements become zero, meaning to say that your normal components or your longitudinal stresses are therefore zero. So these are the normal stresses. And when the normal stresses are zero, it simply means that you are on a pure shear state condition. So this is in contrast with the pure normal stress condition, wherein your shear stresses are zero. So when you are designing a uh, a continuum in terms of a shear failure condition, so you may, okay, you may seek this coordinate axis y prime I such that your pure shear state will be the basis of your analysis. So note that the above is only true if your sum of the diagonal sigma I in the y-I axis is zero, and this is a sufficient and necessary condition for such a pure shear state to exist. So what if this is not equal to zero in the y-I axis? So we can still decompose the stress tensor arbitrarily into a uniform normal stress, which you call it a spherical or volumetric part, and a pure shear or the deviatoric term as follows. So we now have another term here used. So when you say spherical and volumetric, so these are the components upon which your continuum, okay, will experience what you call a change in volume, no? Because of the characteristic of the stresses, which are normal to the surface of this cubical element, then you are expecting a volume change or a spherical change in the behavior of such a component. That's why this term was derived. And when you are in a pure shear state, which is deviatoric, so it has nothing to do with the change in the volume, but rather it has something to do with the change in the angular rotation of your body or your cubical element, since the shear stresses are tangential stresses at the surface. So if we try to look at a two-dimensional scenario here, the shear stresses will not change the volume but rather change the shape. Okay, so if this is a pure shear state, pure shear state, and this is a pure a normal stress state. Okay, so you just imagine the characteristic of the deformation, which is volumetric in this case and deviatoric in this case. So the deviatoric there simply refers to the change in the shape, okay, which has something to do with the shear, okay. So if this will be pulled, no, so the shape will actually be in this form, okay, like this. While here, the tendency for this is to change, okay, the volume and not the shape of your specimen. Okay, so I'd like you to understand very well what these terms are all about, because these are used very often in many cases. Uh, the contexts are just the same, but of course sometimes the formula and the quantity involved is a little bit different. So in terms of the formula, so this is now the formula for your decomposition. So we try to decompose this uh, stress tensor into a volumetric part. This is the volumetric part, and this is the deviatoric part, okay, or the spherical part, and this is the deviatoric shear part, okay. Uh, so the derivation of such is based on the context uh, of simply taking into consideration a balance, okay, effect on the volume change. So I will not go deeper into the detail of this. You just refer to the book of uh, Chang, Frederick Chang, I think, who explained this better than the book of Mays, no? Because Mays is more of a mathematical, the approach is more mathematical, while Frederick Chang is more in the applied, okay, aspect of continuum mechanics. Okay, so of course, if you are trying to decompose the two, the total must be still the same stress matrix or stress tensor, such that if we now back compute the deviatoric part here, we simply subtract the volumetric from the original stress tensor, and we get this one here. So to introduce to you a problem on this, we consider now a stress, sigma ij, wherein the principal stresses were obtained basically the same as that on example 2.9.1, and we yield these results for the principal stresses. Okay, so it is not necessary to convert the original stress tensor on the y-axis, y-axis. This is now converted into a y prime axis on the principal, okay, direction. So you are now in a pure normal shear, normal stress state, okay. Again, it is not necessary to convert the tensor to a principal stress tensor. You can get the deviatoric and the volumetric part of this original tensor if you want. But of course, it will be simpler to interpret in terms of the principal directions. Okay, so Sij, or the deviatoric part now, will simply be equal to the principal uh, uh, stress tensor minus the deviatoric part. Okay, the sigma kk here simply refers to the trace of function, or simply the sigma 1 1 plus sigma 2 2 plus sigma 3 3. Okay, so this is a summation series. Okay, consistently enough, this will just be a scalar, and this is a delta ij here, this is an ij there, and an ij here are consistent. And this is now your matrix values upon which, if we will operate on this, you simply get this principal deviator or deviatoric stress. So if this is not a principal stress tensor, you just remove the word principal there. It's a simple deviator stress. Okay, and take a look. The sum of this is 0, as implied on the condition that this must be 0. Okay. Okay, so we will talk more about this when we go to strains, so don't worry. The principal stresses and the principal strains are simply relative to one another, such that all the concepts and procedures used in obtaining the volumetric and the deviatoric part on stresses will just be the same as that with strains. So thank you very much. I'll see you on the next video for the topic on strains and deformation.